On April 7th, 2020, at the height of the surge in remote working environments worldwide, a security researcher named Keegan Ryan discovered a high-severity vulnerability buried deep within Zoom's desktop application. The vulnerability allowed attackers to inject code directly into someone's Zoom client, changing their settings, including automatically joining meetings without user approval, and joining meetings with both the webcam turned on and their microphones enabled. These changes would be enabled without their permission, persisting indefinitely after someone was attacked, and would be global in nature, applying to every single meeting the client would connect to. The root of this vulnerability was SQL injection. However, this isn't going to be a regular type of injection attack. Zoom did have SQL injection protections in place to protect against this exact type of attack. Also, rather than attacking an SQL database being hosted on Zoom servers, we're going to be attacking the local Zoom desktop application, making this a local SQL injection attack. While you might think that this makes things a lot easier, Zoom is not open source, meaning we can't just read the source code to look for vulnerabilities. The desktop Zoom client has already been compiled from source code to binary by Zoom themselves, meaning that all we have access to is the binary. This seems like it might be nearly useless to us, but that is where reverse engineering comes into play. One of the most basic reverse engineering techniques, known as the strings command, looks through the compiled binary and detects any valid strings of text. If we attempt to search through the binary for SQL queries by using the select keyword, we find several partial SQL queries using format specifiers, which indicate that these queries are composed at runtime instead of using properly hard-coded parameterized queries. A format specifier, such as %s, indicates that the user input is being inserted directly into the raw query, rather than being parsed separately by our database engine. This suggests potential SQL injection issues, but it is far from conclusive. To investigate these queries further, we want to see which queries are being executed by the application. To do this, we want to debug the Zoom application, setting a breakpoint right before the SQL query function. Simple enough. The only issue is we're dealing with a binary, and we can't actually debug binary. Or can we? How do we normally debug a program, especially a compiled language, which is a lot more complex? If you're using a feature-rich IDE, you can just set a breakpoint, click debug, and start stepping through lines without a second thought. But how is this actually possible? Doesn't the source code need to be compiled into binary before it can be executed? And when your code is compiled, all of the defining attributes of the source code that you use while debugging, such as the line numbers and variable names, are both lost. If we're actually executing binary, which has no concept of line numbers, how can we step through code line by line? Same with variable names. There are no variable names in binaries, just the underlying memory addresses. Let's take a look at what your IDE is doing for you under the hood. Debugging code written in a compiled language is going to require an additional step. First, the code needs to be compiled with debug symbols. This is usually achieved by including the -g flag during compilation, if you're using GCC. Debug symbols are additional pieces of information added to a binary that serve as a mapping between the machine code and the original source code. These debug symbols are going to include things such as variable names, function names, and line numbers, essentially acting as annotations. These symbols are the bridge that give you the seamless illusion that you're directly executing source code while debugging. Once the program is compiled with all of these debug symbols, you can now begin debugging with the following command, set your breakpoints, run it, and you'll have access to the next or step commands to progress through your code. All of this happens automatically when you debug using your IDE. Getting back to our Zoom attack, we wanted to see which queries are being executed by the application. Now that we know that we don't need source code to debug, let's go ahead and set a breakpoint at the SQL query function. Again, this may seem simple at first, but even though we don't need the source code to debug, we still do need the debug symbols to tell us where the SQL query function is in the binary, and Zoom isn't so quick to make that public. During the course of development, engineers will compile their code with debug information. However, when it comes time to release the final product, they will release a binary compiled without debug information. This is no surprise, as it would only make closed source code easier to reverse engineer. However, our efforts don't stop here. Using the strings command, we can actually figure out that SQLite version 3.27.2 has been compiled into the application. Luckily for us, SQLite is open source, and its entire codebase is publicly available on GitHub. Using further reverse engineering techniques, such as comparing the known strings defined within specific SQLite functions to strings found within the Zoom binary, we're able to find the location of specific SQLite functions within the Zoom application. Using this technique, we're able to find the location of the SQLite 3 lock and prepare function within the Zoom binary. SQLite 3 lock and prepare is just the function that is ran before any SQL queries are ran against the database. Now that we know its exact location within the binary, we can now set a breakpoint here and watch as the partial queries are filled. Before we go any further, we first need to understand the potential attack vector. Even if there was an SQL injection vulnerability, how would we get our input into a query on somebody else's client? Let's take a look at how meetings are joined in Zoom. The type of link that you click in your browser that causes the desktop app to open the appropriate meeting page is known as a URI, or Uniform Resource Identifier, that begins with Zoom mtg://. This is how the browser and the OS know to open the Zoom application. This URI contains a lot of encoded information, however one of them is the TID, which acts as a meeting ID, informing the Zoom client to which meeting to join. When the Zoom mtg URI is triggered in the browser, the breakpoint is hit multiple times. One of these queries updates a database entry with the long hexadecimal meeting code, which is found to be the exact same hexadecimal code passed as the TID parameter within the URI's encoded data. This now not only confirms that a Zoom mtg URI triggers a database call within Zoom, but it also confirms that the input specified within the URI ends up in the raw SQL query itself. This now opens the door to SQL injection. But what is it? The mid-2000s? No modern-day program is going to have an SQL injection vulnerability. Surely. It was also noted that every time certain sensitive settings were changed, including automatically joining meetings without user approval, and joining meetings with webcam and audio enabled, SQL queries would be sent to the database to save the state of these settings. This is what could make an SQL injection vulnerability especially powerful and dangerous. Now that we know that information from the URI ends up in an SQL query, this is the moment that we've been waiting for. The classic SQL injection that we've been warned about for our entire lives. As mentioned before, it looks like these queries are using format specifiers, as opposed to being properly parameterized queries, which is a textbook case of SQL injection waiting to happen. All we need to do now is to enter a single quote to break out of the string, and then we're free to run whatever queries we want against the database. For example, we can enter a semicolon to start a new query, drop an entire table, and end it off with a comment, invalidating the rest of the command. Of course, Zoom isn't going to make things this easy for us, as Zoom employs some SQL injection protections. Anytime a user tries to close a string with a single quote, another quote will be automatically added, opening another string, resulting in invalid SQL syntax. Common sanitation bypasses, such as trying to include a backslash character, also fail. While it may appear that Zoom is doing a decent job at protecting against common SQL injection attacks, it is susceptible to a much more obscure type of attack. In order to understand this type of attack, we first need to understand character encodings, beginning with ASCII, Unicode, and UTF-8. As you might be familiar with, ASCII, or the American Standard Code for Information Interchange, is a mapping that uses 7 bits to encode 128 different characters. A capital A is encoded as a 65 in decimal, or OX41 in hexadecimal. A lowercase a is encoded as a 97 in decimal, or an OX61 in hexadecimal. ASCII quickly became the standard for English-speaking countries. However, 128 characters simply wasn't enough to suit everyone's needs. What about other languages? Characters with accents, special characters, and even emojis. This is where Unicode steps in. Unicode is a new and improved standard that expands the number of characters being covered from 128 to about 150,000. This is great, however it introduces one massive problem, being encoding size. To represent 150,000 different characters, to be on the safe side of things, each character would need to be about 32 bits. Something else to mention is that Unicode was intended to be fully backwards compatible with ASCII, meaning that a capital A is still represented as a 65 and a lowercase a is still represented as a 97. This means that you would have a heartbreaking amount of leading zeros before any English character. Suddenly, every single English language text file takes up 4 times the amount of space on your disk, and every single English language website now takes 4 times as long to load. This is incredibly wasteful. We somehow need an encoding method that removes all of these zeros, yet is still fully backwards compatible with an ASCII-only system. Now, Unicode is just a mapping standard, mapping characters to numbers. It doesn't actually define any sort of encoding method. What I just described, where each character is of a fixed size, such as 32 bits, is known as a fixed width encoding scheme. Luckily, there is another option, known as a variable width encoding scheme. The variable width encoding scheme, known as UTF-8, is now the most widely used, accepted, and supported Unicode encoding schemes in the world. Nearly every piece of text you read and type is used with UTF-8 encoding. But how does UTF-8 actually work? Simple. We know that we might need to use up to 32 bits to encode the full Unicode range, which is 4 bytes. However, if we can fit something into a lesser amount of bytes, we only want to use that number of bytes. The number of bytes that are being used by a character is going to be conveyed to us with special control bits at the start of the first byte. Let's go over an example. If you want to use UTF-8 to encode a single byte character, we begin the byte with a 0. This signals that the character is a single byte long. The remaining bits will then be treated as data, and we can enter the following, which is a 65, to represent a capital A. If we wanted to encode a 2-byte character, we would begin the first byte with 110. This signals that the character is 2 bytes long. For any subsequent bytes, we use 10 as control bits just to signal that this is a subsequent byte. This is the format for a 2-byte character, and the rest of the bits are interpreted as data. Triple 10 is used to signal a 3-byte character, and quad 10 is used to signal a 4-byte character. This is where our exploit comes into play. Let's try and break out of our string within the SQL query. For our input, let's use OXC2 followed by a single quote. This is the binary representation of OXC2. Notice anything special about this? This represents the beginning of a 2-byte character. This means that when a UTF-8 decoder sees OXC2, it's going to go ahead and look for the next byte before determining the character. By the way, \x is just an escape sequence used to represent a character in hexadecimal. Here's where things start to come together. The Zoom application does not decode anything. It interprets all of this as plain text and injects the second quote as part of its SQL injection protections. This is exactly what gets sent to the database. The database, however, does attempt to decode the string. When the database sees OXC2, it is signaled that this is the first byte in a 2-byte character and moves forward to read the second byte. The second byte, as we can see, is just a single quote, which is represented as OX27 in hex, or as the following in binary. As we now know, this is not actually a valid second byte, as all subsequent bytes must begin with 10. The UTF-8 decoder will actually end up assuming that the first 2 bits are 10. This results in the second byte being treated as the following in binary, which is OXA7 in hexadecimal. The final result of our OXC2 and single quote is now calculated as a singular 2-byte character, C2A7. This then gets decoded to the section sign character as per Unicode standards. This entire process completely eliminates one of our single quotes from existence, leaving only one remaining single quote, which ends up closing our string. We are now free. We did it. Any other text that we include outside of the single quote will now be directly interpreted as an SQL query. Now we can go ahead and update user settings, as we can see here. Keegan showcases this by having one malicious link perform the injection, permanently changing the user's settings on the client. Afterward, he joins a regular meeting, and sure enough, he joins with his webcam on. After an initial bug report was submitted to Zoom on April 7th, it was triaged as high severity and patched shortly afterwards. If you're interested in more vulnerability breakdowns, check out these videos, and subscribe to the channel for more content. Thanks for watching.